Hello there. In this video, we're going to work through a couple examples on probability. The first example is going to be a little bit more easier than the second. And also for the second example, we're actually going to prove a couple more additional properties that are a little bit more deeper and calculus-based as well. So let's consider this first example to start off. Suppose you roll a 5-sided die, put it in your left hand, and a 7-sided die and put it in your right hand. What is the probability that the value in your left hand is greater than that of the value in your right? So if you want to give this example a try before we start to work through the solution, I definitely invite you to do so. But this video is going to be based on how to solve probability problems in, a basic and intuitive way. Alright, so this problem is a little bit more straightforward than some other more complex ones, say for example a deck of cards kind of example. So what we're going to do is we're going to try and solve it very directly by first mapping out the sample space of all possible events. So the values in our left hand can range from 1 to 5, and the values in our right hand can range from a 1 to 7. So we're going to assume that S is going to be the set of all values in the form x comma y, such that x belongs to the left hand and y belongs to the right hand die. So that means x belongs to the set 1, 2, 3, 4, and 5, and y belongs to the set 1, 2, all the way down to 7. So what is the sample space going to look like? So if this is the case, that means S is going to have the values 1, 1, 1, 2, all the way down to 1, 7. Then we can go to 2, 1, 2, 2, all the way down to 2, 7. Let's not close the brace because that's not the whole set, comma, comma. And let's continue in this fashion. So we're going to go all the way down to 5, 1, 5, 2, all the way over to 5, 7. And that's going to be all the values. So of course this is a square matrix where we have 5 along the 5 rows and we have 7 columns. So it's very easy to see that there are 7 times 5 or 35 values inside of S. So now let us map out the event space. So the event space is going to be the set of all values x, y, such that x is bigger than y. So we want the left hand to have a greater value than that of the right hand side. So what values in this sample space are going to make that true? So 2, 1 is going to be in there. Say 3, 1, 3, 2 is also going to be in there. And once we get down here, we have 5, 1, 5, 2, we have 5, 3, 5, 4 in this last row. So let's map out all of them. So 2, 1 is the first value because 1 is not greater than 1, 1 is not greater than 2, so the entire first row of our sample space will not be included. And 2, 2 will not be included because 2 is not greater than 2. So then we have 3, 1, 3, 2 in the third row. We have 4, 1, 4, 2, and 4, 3 in the fourth row. 5, 1, 5, 2, 5, 3, and 5, 4 in the last row of our sample space. So this is our event space E. So therefore, the size of E is going to be equal to 1 plus 2 plus 3 plus 4. So that's going to be equal to 1 plus 2 is 3 plus 3 is 6 plus 4 is equal to 10. Now keep in mind, this is a sum of natural numbers, namely the sum from k is equal to 1 to 4 of k, which we know has a general formula. So if this problem is a little bit more complex, you may want to use the relationship, the sum from k is equal to 1 to m of k to be equal to n times n plus 1 divided by 2. So this is one of those examples where this sum formula may come in handy. And typically anytime you have a triangular type of event space or sample space, this formula definitely may be of use. All right, so therefore the probability of our event occurring is going to be, by definition, the size of E divided by the size of S. So E we found to be equal to 10, the size of S we found to be 35. So this is going to reduce to 5/7, which we should know to be approximately equal to 0.714. So it's about a 71% chance that the value on the left is going to be greater than the value in the right. Actually, no, that's not true. That should be 2 out of 7, right? Yes. Basic example. So what is that? That's about 2.286, I think. Yeah. All right, so that gives us that first basic example. So now let us take a moment to write down the next example. So let us assume that there are 5 people in a room, and each of them have a colored ball, or a particular number on a piece of paper, or a different hat. And let's assume all of these objects are different, and they throw it in the middle of the room. And then everybody randomly selects an object from the middle of the room. What is the likelihood that no one chooses their own object from the middle of the room? All right, so let's map out this solution the best we can. So, solution. So let's define some notation. So we're going to let EK represent the event that person K, so K is going to range from 1, 2, 3, 4, or 5, does not choose their own ball. So we're going to try and figure out the probability of E, which is going to be the probability of E1, union E2, union E3, union E4, union E5. So we're going to try and figure out a couple of small things first. So what is the probability of EK? So the probability that no one chooses their own ball, and let's assume they're mutually independent, just for this example briefly. So if there's 5 objects in the middle of the room, what's the probability that they choose something else that's not theirs? So that's going to be 4 out of 5, and that's going to be for K is equal to 1, 2, 3, 4, or 5. So this is if they are independent. So a couple questions that we need to ask ourselves. Are E1, E2 down to E5 independent? So in general, since P1, so person 1, could not possibly be getting their own object, let's call it ball. So if they not getting their own ball has happened, then this affects another person of getting their own ball or not getting their own ball. So this definitely has some effect. So in general, the answer will be no. So are E1, E2 down to E5 mutually exclusive? So what does it mean to be mutually exclusive? So that means they cannot happen simultaneously. So is it possible that E1, which means the event that person 1 does not have their own hat, and person E2 does not have their own hat, is it impossible that these events can happen simultaneously? The answer to that is no. So they can happen simultaneously because all of the people could select their own hat. So for that reason, the answer to both of these is no. It is not independent, it is not mutually exclusive. So our simplifications of some of the formulas will not happen in this case. So let's see if we can figure out the general formula for what we want to go for. So let's recall the sum rule for probabilities, namely the probability of A union B is equal to the probability of A plus the probability of B. And let's assume that A and B are not mutually exclusive, therefore we need to subtract off the intersection, because it's definitely, in this case, they could happen simultaneously. So this is the sum rule for two events. So there is a sum rule for three or more events. So let's look at the three case. So A union B union C. So this is going to be equal to the probability of A plus the probability of B plus the probability of C. And then we need to minus the probability of A intersection B minus the probability of B intersection C minus the probability of A intersection C, and then plus A intersection B intersection C. So that would be the sum rule for three events, and you can extend this to more cases, of course. So of course, an important observation, notice that these signs in front of our single sets, double sets, and triple sets alternate between plus and minus sign. So let's see if we can sort of generalize this notation just a little bit. So the probability of the union from k is equal to 1 to 3, and I'm going to call these sets A, B, C as E1, E2, and E3 before we generalize this a bit. So we first have the sum from k is equal to 1 to 3 of the probability of EK. And then we have minus the sum from k is equal to 1 to 3. Let's see, best way to do this. Let's do the sum across all values k less than j of the probability of EK intersection EJ. Because this is E1, E2, E2, E3, E1, E3. So of course 1 is less than 2, 2 is less than 3, 1 is less than 3. So this will be true as long as k and j are both between 1 and 3. And then let's do plus. So this is going to be the probability of the intersection from k is equal to 1 to 3 of EK. And then of course this alternates between these two objects. So this is the intersection of one set, intersection of two sets, intersections of three sets. So I'm going to pretty much generalize this in just a moment. All right, so let's see here. So remember one of the properties that we proved before, the probability EK is going to be equal to the probability of EJ for all k and j in the natural numbers for the general case. Even though we only go up to 5, this is going to be true for the general case. So these values, for example, here are going to be the same. Same for the values here, that are also going to be the same. So the probability of E1, E2, E3, they're all the same. The probability of E1 and E2, E2 and E3, E1 and E3, they're all going to be the same as well. So we're actually summing up the values, even though the values are the same. We can actually just write the sum as multiplication, and that's of course 1. So what we can do, so we can rewrite the probability from UK is equal to 1 to 3 of EK to be equal to 3 choose 1 of probability of EK minus 3 choose 2 of the probability of the intersection k less than j of EK. And this is all our two sets. And then this is plus 3 choose 3, which is of course 1. And this is the probability of the intersection, of course, k is less than j, less than L. This is all combinatorial product intersections of 3 sets. So 1, 2, 3, 1, 2, 4, 2, 3, 4, and all those types of things. And of course, this is the single intersection for this first case. So for k is equal to 1, 2, 3, all the way down to n, we have the following property. So the probability for k is equal to 1 to n of ek can be generalized for this particular example to be the following thing. So the sum from k is equal to 1 to n of n choose k. Now, of course, notice that this does alternate from 1, minus 1, 1, minus 1, 1, minus 1. So it starts off positive and k starts at 1, so I need to increment this by 1. And we have the probability, let's do the intersection from L is equal to 1 to k of E sub L. So this expression right here, so where the probability of the intersection from k is equal to 1 to n of EL, so this should be L is equal to 1 to L is equal to 1 to n. So one can find out by the fundamental counting principle that this is just going to be equal to n minus k factorial divided by n factorial. So that's by the fundamental counting principle and some combinatorics, some basic combinatorics. So let's sort of illustrate this little example. So let's assume that k is equal to 3 and n is equal to 5. So you have 5 possible outcomes, and you have 3 people who sort of throw their hat. So the probability of E1 intersection E2 intersection E3. So we have 5 factorial ways. So 5 for the first, 4 for the second, 3 for the third, 2 for the fourth, and 1 for the fifth. So you have 4 for the first person because that person can't select the fifth one. Now one person's already selected the hat. Now we have 3 down, and then we have 2 remaining hats for the last person to select, where one of them cannot be his, right? So it's always one less than we have, and that's going to give you the probability of that event for this particular problem. So let's replace that into our generic formula. So the probability for mu is equal to k equals 1 to n of ek is going to be equal to the sum from k is equal to 1 to n. So we have m factorial over k factorial times m minus k factorial. And then we have negative 1 to the k plus 1 times m minus k factorial over k factorial. So this, remember, is our n choose k. And this right here is the probability of the intersection of our ek formula. And this is the negative 1 that oscillates the terms of our sum. So what do we have here? So we should see, that bottom should be n factorial. What's he doing there? So we have an m minus k factorial, which of course cancels. Our n factorials cancel as well. So we have a nice compression here. K is equal to 1 to n of ek. So it's going to be the sum from k is equal to 1 to n. What do we have? So we have an alternating series of 1 over k factorial. All right, so what does this sum look like? So this is 1 over 1 factorial minus 1 over 2 factorial plus 1 over 3 factorial minus 1 over 4 factorial plus minus all the way up to, now the last term could be positive or negative, we don't know, so that's going to be negative 1 to the n plus 1, 1 divided by n factorial. So that's pretty much what this sum is. What we can do is we can sort of add 0, and you may not know why I'm doing this, but if you actually want the answer to the original problem, we're just going to set n is equal to 5, and that's going to give us what we want. But what I'm going to do is I'm going to play around with this formula because this should look a little bit familiar. So I'm going to do 1 minus 1, and then I'm going to, so this is just 0, so I'm not really changing anything. Factorial plus minus plus 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 negative 1 over n factorial. So what I'm going to do is I'm going to factor out a negative 1 out of all of these terms. So I have 1 minus, so that's negative 1 is going to be plus. Then this plus is going to be minus 1 factorial minus plus 1 over 2 factorial minus 1 over 3 factorial plus minus all the way up to, now this last term, of course, is going to be negative 1 to the n plus 2, which is just the same thing as negative 1 to the n of 1 over n factorial. And keep in mind, we can rewrite this as 1 over 0 factorial as well. So what I've done is I've written this in the form, the sum from k is equal to 0 to n of negative 1 to the k, 1 over k factorial. So this is the probability of the union from k is equal to n over ek's. So what we have is the sum from k is equal to n of ek. So what I'm going to do is I'm going to multiply and divide by n factorial. So this is going to be n factorial over n factorial. So we have 1 minus 1 over n factorial times n factorial times the sum from k is equal to 0 to n, negative 1 to the k, 1 over k factorial. And this precisely is the subfactorial of n. So that means the probability of our event, or the general event, is actually equal to 1 minus n subfactorial over n factorial. This is a beautiful compact relationship. So therefore, our particular example is n is equal to 5. So that means the probability of the union from k is equal to 1 to 5 of ek is going to be equal to 1 minus 5 subfactorial over 5 factorial. So remember, 5 subfactorial is equal to 44, and 5 factorial is 120. So this is going to be equal to 76 over 120, which is about 63%. So that gives the answer to our relationship. So last property that we've actually derived here, so a side note. So the probability of this particular event, where you sort of throw n hats into the middle of the room and you want the probability that no one selects their own hat, so we found this interesting identity. So what we can do is do the following. So if you learn about Taylor series, this should look familiar. We can rewrite this as negative 1 to the k times x to the k over k factorial. So if we evaluate this at 1, we get the expression above. So what this is actually, so we can do 1 minus the sum from k is equal to 0 to n. So notice negative 1 and x have the same exponent. So this is negative x to the power of k all over k factorial. Evaluated x is equal to 1. So therefore, we have this property that the probability of the union from k is equal to 1 to n of ek is equal to 1 minus the sum from k is equal to 0 to n of negative x to the power k over k factorial, evaluated at x is equal to 1. So the interesting property for this problem actually occurs as n gets arbitrarily large. So what we can do is take the limit as n approaches infinity of both sides. So we have the probability from the union from k is equal to 1 to n of ek is going to be equal to 1 minus the limit as n goes to infinity. First term doesn't have n, so I can pass that over, of the sum from k is equal to 0 to n of negative x to the power of k over k factorial when x is equal to 1. So we have the probability from u from k is equal to 1 to infinity of ek is going to be equal to 1 minus the sum from k is equal to 0 to infinity of negative x to the power of k over k factorial, evaluated at x is equal to 1. Now, if you're familiar with some basic differential calculus, this is the Taylor series for the exponential function. So therefore, the sum from the union from k1 to infinity of ek is going to be 1 minus e to the minus x, evaluated at x is equal to 1. So therefore, this problem, union k is equal to 1 to infinity of ek, is precisely equal to 1 minus 1 over e, or equivalently e minus 1 over e. So that means this original problem that we had that started with 5 people, if you add more people to this game, like 500 people, and they all throw their hat in the middle of this room, then the probability will get closer to this special number, which is really cool. So also remember, we had another representation for this. So we have the limit as n goes to infinity of the probability of u from k is equal to m, vk, which is equal to e minus 1 over e, is going to be equal to the limit as n goes to infinity of 1 minus n factorial over n subfactorial over n factorial. So remember, this is the same as 1 minus 1 over e. So looking at this term, we can sort of subtract both sides of this equation by 1 and ignore the equal sign. So we have the very interesting limit that sort of comes out as a consequence. The limit as n goes to infinity of n subfactorial over n factorial is actually equal to 1 over e, which is a very beautiful result. That pretty much says that, n factorial and n subfactorial sort of grow at the same exact rate because it doesn't really go to 0. So n factorial sort of, grows at the same rate, but just a little bit bigger or something like that. So this is pretty interesting. So this is just a couple examples on probability. The first one's pretty easy. The second one's a little bit more detailed, but we've derived a more general conclusion as also developed some theoretical properties along the way. Hope you enjoyed.